Unit for review, Problem 6. The Fish and Game Department stocked Lake Loomis with fish according to the following percentages: 10% catfish, 30% bass, 40% bluegill, and 20% pike. 5 years later, they sampled the lake to see if the distribution of fish had changed. Of the 500 fish in their sample, 62 were catfish, 108 were bass, 204 were bluegill, and 126 were pike. Use the chi-square test to determine whether the distribution of fish in Lake Loomis had changed significantly over this 5-year period. Based on this result, what conclusion should the Fish and Game Department reach? Well, first we're asked to use a chi-square test to determine whether the distribution of fish in Lake Loomis had changed. Well, there's two versions of the chi-square test. There's the chi-square test for independence and the general chi-square goodness of fit test. Here, since we're looking at whether the distribution of fish had changed in Lake Loomis or not, that is, whether they stayed the same, kind of fit, or change, they're different, don't fit, we will use the chi-square goodness of fit test to answer this question. So in order to conduct a chi-square goodness of fit test, we need to go through our 5-step hypothesis test procedure. The first step in any hypothesis test procedure is to state the hypotheses. We label the null hypothesis H0 and the alternative H1. And in the chi-square goodness of fit test, the null hypothesis, HO, is always the same. It's that all of the expected frequencies fit the observed frequencies. HO, the null hypothesis, always includes the condition of equality, and fitting basically means they're essentially equal to one another. So in the chi-square goodness of fit test, HO is always that all of the expected frequencies fit the observed frequencies. And H1, the alternative, is the opposite. Not all the expected frequencies fit the observed frequencies. So now that we've stated our hypotheses, HO and H1, we get to go to step 2, where we identify alpha, the level of significance. It's customary to use a alpha of 0.05 or 5% when conducting any hypothesis test, unless stated otherwise. Since there was no level of significance given in this problem, we will use the customary alpha of 0.05. Next step is where we use our sample data to calculate the p-value, which we can then use to make our decision and reach a conclusion. The data that needs to be entered in the chi-square goodness of fit test are both the observed frequencies and the expected frequencies. The observed frequencies comes from the actual sample data. In this case, their sample of fish that was collected 5 years after the lake was stocked. And then the expected frequencies are always based on the n times p, n the total sample size times p the hypothesized percentages. Those expected frequencies, n times p, are entered in the second list, list 2. All of these values are given here in the problem. So we'll go through this to set up our list 1 of observed frequencies and our list 2 of expected frequencies. First, we note that there are 4 categories of fish in this problem. We have catfish, bass, bluegill, and pike. The observed frequencies, or the sample data that's entered into the first list, comes right from the sample. So here when it says, of the 500 fish in the sample, 62 were catfish, we can enter the observed 62 number of catfish. And 108 were bass. So the observed frequency for bass was 108. The expected frequency of bluegill was the 204 bluegills that were caught in this sample. And finally for pike, there were 126 pike observed in this sample. So now that we have our observed frequencies, the actual sample data, we then turn to calculate the expected frequencies. which are calculated by taking n, the total sample size, times p, the hypothesized proportion or percentage. Here n, the total sample size, is the 500 fish that were in the sample. So we'll use n equals 500 to calculate each of these expected frequencies. Here the problem actually gave us the total sample size of 500. If the problem didn't actually give us this total sample of 500, we could still figure it out by looking at the total or the sum of the observed frequencies. Here, if you add the 62 catfish plus the 108 bass plus the 204 bluegill plus the 126 pike, you'll find that it equals a total of 500 fish in the sample. So here we'll take the n of 500 and multiply it by p, the hypothesized proportions or percentages. Starting with catfish, we're told that Lake Loomis was stocked with 10% catfish. So we'll use the 10%, or on the decimal calculator, 0.10, and take 500 times 0.10 to get the expected frequency of catfish. 30% were bass. So P is the 30%, or 0.30 decimal. To get the expected frequency for bass, we take the total sample of 500 fish times the 0.30 proportion that were bass. 40% were bluegill. So we'll take the n of 500 times the p of 0.40 for bluegill. And 20% were pike. So we'll take the n of 500 times the p of 0.20 to represent the 20% of the fish that were pike. So entering in these n times p values into the second list, we get the expected frequencies. So we find that we expected to have 50 catfish in this sample, 150 bass, 200 bluegill, and 100 pike if the proportions 5 years later were actually to remain the same or not change over this 5-year period. So in the calculator, we could enter the observed frequencies in list 1 and the expected frequencies in list 2. And with the data entered into the lists, we can then use the chi-square GOF test command to calculate the p-value we need. To calculate the p-value using the chi-square GOF test on the TI-84 calculator, we press Stat, arrow over to Tests menu, and then arrow up till we find the chi-square GOF test command. Press Enter. Here we've entered our observed values in list 1. Second one, Enter. We've entered our expected values into list 2. Second 2, Enter. DF, the degrees of freedom in a chi-square goodness of fit test, is the number of categories. In this case, there were 4 categories of fish. -1. Enter gives us 3 degrees of freedom. And then with the cursor blinking on Calculate, we press Enter, and we get our results. So now that we've calculated our p-value, we can then reach our decision. All hypothesis test procedures make the decision the same. We either reject the HO when the p-value is less than or equal to alpha, the level of significance. Otherwise, we do not reject the HO. And after we made our decision to reject or not reject HO, we then need to state the conclusion or answer the question, where's the problem, interpreting what the reject or not reject conclusion means in this context. So the p-value for this problem is equal to 8.367 e minus 5. The e minus 5 means that decimal place between the 8 and the 3 needs to be moved 5 places in the left or the negative direction. So we'll have 5 zeros as 0.00008367. And when rounding the p-value probability to 3 places after the decimal, it essentially rounds off to 0. And since the p-value of 0 is less than or equal to the alpha of 0.05, we can make our decision. Since the p-value of 0.000 is 0.05 or less, the decision is to reject HO. Now, HO in the chi-squared goodness of fit test is always that all of the expected frequencies fit the observed frequencies. And since we decided to reject HO, the conclusion is the idea in HO is not valid. So therefore, we should not conclude that all of the expected frequencies fit the observed frequencies. Instead, with HO rejected, we turn to H1 as the valid result. So here the conclusion should be that not all of the expected frequencies fit the observed frequencies. So therefore, not all of the expected frequencies fit the observed frequencies. And when not all of them fit, they're basically saying not all of them are equal. And so to answer the original question, can the Fish and Game Department reach the conclusion that the distribution of fish in Lake Loomis had changed significantly over this 5-year period? The decision to say that they do not fit means they're basically not equal to what they were 5 years ago. Therefore, not equal means they are different or had changed. So, based on this result, the Fish and Game Department should reach the conclusion that the distribution of fish in Lake Loomis had changed significantly over this 5-year period. Now, a conclusion to any hypothesis test can only answer in that yes or no, yes it had changed, or no it had not. In this case, it's yes it had changed. And that's the extent of what we can get out of the hypothesis test. If you want to get any indication as to exactly how the distribution of fish had changed over this time period, we need to look inside the data. So, looking at the catfish data, we expected 50 if things had not changed, but we actually had observed 62 5 years later. This is a pretty big increase. So we could say that the number of catfish in Lake Loomis had actually increased somewhat over this time. Looking at the bass, where we expected 150, but actually observed 108, 108 is significantly lower than the 150 that were expected. So we could actually say that the proportion of bass in Lake Loomis had actually declined significantly over this time period. Looking at the numbers for bluegill, where we expected about 200, but actually observed in a random sample 204, this is really not significantly different at all. It's essentially the same. So the conclusion can be that the bluegill pretty much has stayed the same over this time period. And finally, looking at the data for pike, where we expected 100, but actually observed 126, 126 is a significant increase above what we were expecting. So here we can conclude that the proportion of pike had actually increased significantly. So when looking inside the data, we can conclude that the data indicate that the proportion of bass had decreased while the proportion of pike had increased. And this helps to explain how the distribution of fish in Lake Loomis had changed significantly over this 5-year period.